Greetings, calculus students. Yesterday, we talked about what a series is and what a sequence is and how they can sometimes converge to finite numbers even though they are infinite in length. And the rest of this unit is about seeing when that happens, trying to test what series can converge and which go off to infinity. And today we're going to look at some simple patterns that you can follow to notice very quickly whether they converge or not. I'm going to kind of go off order from how things like AP Classroom or Khan Academy might do things, because I think that these basic types of series are easier to recognize than any scary algebraic or calculus-y tests that you'll do later on. So let's look at some basic rules to start out with. When you think about how an infinite list of numbers can come to a finite sum, how can that happen? The only way that can happen is if our numbers, which I'm going to represent by these boxes, if we're just adding up a bunch of boxes that go on for infinity, we're going to get a really, really big box. But if the boxes, each time we add them, get smaller and smaller and smaller and smaller and smaller until the infinitieth box we add is basically no box at all, you can see how this infinite sum can kind of stop gaining bigness, right? Because the infinitieth plus 1, if we go one more, it's basically adding 0, and so we've reached our finite sum. And so the only way, just logically, intuitively, the only way that an infinite series can have a finite sum is if the limit of the series, the biggest the series, or what the series gets to as you go down the list, is 0. So you'd write this as the limit as n approaches infinity of a sub n has to equal 0. Now, we get a little bit funky. Just because the limit of a sub n equals 0 does not necessarily mean it converges. And we're going to get to some counterexamples later in this video and some proofs of that in the next video. But we know that in order for any series to converge, the first criteria for a series to converge is that the limit of a sub n equals 0. And since we know that, we can say the opposite. If the limit of a sub n does not equal 0, it's really easy to say this thing does not converge. There is no way that the sum of a series that goes somewhere other than 0, there's no way it converges. And so I've written this as a simple equation that you might want to memorize and really try to understand. Big equals bad. If the numbers get big, the series is bad. That's your lesson for today. But this doesn't necessarily mean that the numbers have to go off to infinity. In some cases, the series will go off to infinity, because if our general term a sub n equals n, so our series looks like this, 1 or 0, 1, 2, 3, ... Then the sum of this, our sum, since each term goes off to infinity, right? The infinitieth term, the limit, as n approaches infinity, of a sub n equals infinity. And so that's really easy to say that when you add up a bunch of things that eventually get super big, the sum gets super big. But even if we have a list more like this, where you've got 1.1, 1.01, 1.001, etc., then our limit of a sub n is clearly approaching 1. And our little graph is going to not look like something that goes off to infinity, but it's going to look like this nice little asymptote that is the values of the series are converging to 1. The values of the sequence are converging to 1. But the sum of the series, if we think about it, right, we're adding up all of these numbers. And even though the numbers are going somewhere, the numbers are going towards 1, we're thinking about adding them all up. So we're thinking about like this stuff. The area under the curve is a way that I kind of think to visualize it, and we're going to talk a little bit more about this later, right? Because we're adding up the values of all of these lines. And eventually, we're just going to get something that looks like 1 plus 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 1. And if you add up 1 infinity times, that's infinity. That's really big. So this idea that a series with a limit that a sequence with a limit that does not equal 0 diverges is sometimes called the nth-term test for divergence, which is absolutely hilarious. Like, they took a very simple concept, big equals bad, and turns it into those words. But you can kind of see where it's going. They're saying the limit of the nth term is like kind of what we're looking at. Like, this is like the nth term of the series. And it's not a test for convergence because it doesn't necessarily converge if it does equal 0. And so you can kind of see where the name nth term test for divergence comes from. But like, other than the fact that if they ask you for that on the calculus test, you don't have to know it's called that. Big equals bad. The next basic form of series we're going to look at, we've already seen a little bit in the last video. I used it as an example because it's something that we can kind of understand pretty easily. It's called a geometric series. And it would look like this. It'd be like our a sub n is going to look like some constant. I'm going to call it c. They sometimes call it a in like calculus resources, but I think that's confusing because we often call the series a. So I'm calling this constant c because constant c makes a lot of sense to me. It's c times some constant ratio r raised to our nth power. And that looks kind of complicated, but really what it'll be is like an example. If we say that c is 1, we don't worry about the constant right now. We can look at our example from before, 1/2 to the n, which we saw does converge. We demonstrated that 1/2 to the n converges to 1 if you start with an n of 1. And so you'd write the sum of this series as n equals 0 or 1 or something. This is something that can trip people up, is that the start of the series can be in different places. But let's not worry about that right now. The sum of the series from n equals 0 to infinity of some constant times the ratio to the nth power. And this is going to look like, as in the case of 1/2, it's going to look like, or if we write it in our general term, it's going to look like our constant plus our constant times r plus our constant times r squared plus our constant times r cubed. And so the series, or the sequence, is just increasing by a power of r every time. You're multiplying r to each term of the series to get to the next term. And it's easy to see, just like how we were just talking about, if r is anything like 1 or bigger, this is going to get huge. Like if r is a positive number like 2, then we're going to have, if c is 1, let's ignore c for now, and if r is a positive number like 2, our series is going to look like 1 plus 2 plus 4 plus 8 plus 16, and that's not okay. That's going to get really, really, really big really fast because powers of 2 go up really fast. But the inverse is true. Not only do positive powers go up really fast, fractional powers go down really fast. And so as we saw with 1/2, 1/2 plus 1/4 plus 1/8 plus 1/16 goes to 0 really quickly. And like very quickly is going to have like gains to this sum that are not like significant enough to make it go off to infinity. And so these geometric series, this sum of c times r to the n, will converge if r is less than 1. And of course, you can't include 1 in that, because if r is 1, 1 to the nth is always 1, and so it's just going to be our constant added up over and over again, which is, of course, infinity. So this converges if r is less than 1. And there's something special about geometric series. Unlike almost any other series we work with, a series in this form is one that we can actually know the number that it converges to. Most of this unit is going to be just seeing whether it converges or not, but this time we can actually like see where it's going. And there's a formula for that. You can say that the sum of this series equals our first term. So I'm going to call our first term a sub naught, which would change, like it's not necessarily a 0. So I'm going to call this like a of first term, because putting any number there could change this value. So like if we started this series at 2, then it'd be the second term, or like when n equals 2. The first thing in the list, when you've got a list of the numbers, like this, when we had that 1 plus 1/2 plus 1/4, the thing on top would be the 1. But if we ignored that and started with the 1/2, then the thing on top would be the 1/2. It's the first term of our little list. And on the bottom, we have 1 minus our common ratio. And so this is actually what the series will equal when you add it up to infinity. And in the next video, I'm going to have a little proof for that. The next video is going to be a fun little optional side thing where we prove a couple of things I talk about here. The next type of series we're going to look at is another basic series that uses like similar logic to see how it gets really small really fast. This is called a p-series, and it's written like this. The general term of our sequence is 1 over n to some constant p. I don't know why they chose p, but apparently they call it p, and the whole thing is called a p-series. If it was an x, you could call it an x-series, but they don't. They call it a p-series. And a p-series like this, you can see how since we've got an exponent in the bottom, it's also probably going to get small really quick. But if the exponent is less than 1, if we had the sum of 1 over n to the like 1/2, which is the same as 1 over the square root of n, it's still approaching 0. And this is one of those cases where even though the limit of the sequence, like 1 over the square root of infinity, is 0, but when you add it all up, they don't get small fast enough. Like when we're adding up these boxes, the boxes are still like of significant size for a very long time. And so it doesn't actually converge on a finite sum. And so this p-series, which looks like this, will always converge if p is greater than 1. Because if we've got like the sum of 1 over n squared, that's going to be like 1 plus 1/4 plus 1/9 plus 1/16. And you can see how this also gets small really fast and will converge on a sum. Unlike the geometric series, however, we can't tell where this actually goes. We can estimate it, but we can't tell where this actually, what do you?
Move the board.
Move the board?
It's going off.
I've been rolling the, I forgot to lock the wheels. Guys, I forgot to lock the wheels. When the thing gets really small, it converges. And when p is greater than 1, that's when that happens. You've really ruined my mojo.
They're going to be so entertained.
They're going to be very entertained. There is a special case to this series. And it's super simple looking. But it is kind of important to think about. What if we have the sum of just 1 over n? Which is about in the same form as a p series, but p equals 1. We know that this converges if p is greater than 1, but what if p actually equals 1? And this is the first funky little thing that you'll encounter in this course, where even though this looks a whole lot like it's approaching 0, like it's going to go down like this towards 0, it doesn't quite reach there. And this was pretty cool to some people in ye olden days, and so they decided to give this very simple series its own fun name. This series, 1 over n, is called the harmonic series. And it does not converge. The harmonic series diverges. If you've learned anything, the harmonic series diverges. Always remember that the harmonic series diverges. In the next video, I could prove to you that the harmonic series diverges, but for now, and if you don't want to watch the proof, that's kind of optional, just know that the sum of 1 over n always diverges. It's called the harmonic series, and it does not converge. As I've been saying, in the next video, I'm going to do quick little proofs for why a geometric series has the sum first term divided by 1 minus the ratio, and also why this simple looking series that does seem to approach 0 doesn't actually converge. Bye-bye. Bye-bye.